We ready to go? Everyone's got... Okay, let's take a few notes here. All right, so as you can see your topics, I want to do a quick review of the Law of Sine. Just do maybe a problem or two, just kind of refresh your memory. Talk about kind of where it originated from. That's something I didn't really discuss yet. And then we're going to get to our new stuff, which is something I introduced the Friday before spring break. And I said this is what we're going to next week, or when we're back. And this, I want to go through at least a formula of this, like a problem or two with that. And then we'll get to the more difficult stuff later this week with this stuff. Because there's going to be eventually a story problem that I'd like us to solve here with these. And we're going to need to know how to use them and do some pretty complicated math, which these formulas are not complicated, but the stuff we're going to do with them can be pretty wild. So we'll see that later this week. So I think this week is kind of a fun one in terms of like realistic uses for this.
What did we do last Friday?
We did Law of Sine. We did like an example of that, and we introduced the Law of Cosine, which is a new formula. So we're going to do that today, but I want to review that today. So let's talk about the Law of Sine, because I really didn't talk about where this came from, and I think that's important today. All right, but yeah, let's get rid of the computers. We don't need the computers right now, so let's get rid of those. So, you want to get rid of the computer? Thanks. All right, so let's talk about the Law of Sine here. So, real quick, let's draw this out, just so you can get an example of this. All right. Just kind of making up some numbers here. Let's go with this is 70, this is 80, this is X, this is a 24. This is just a quick example. It's something that we did, the couple days before, break. Okay, so on this problem, this is a non-right triangle. How I can prove that? What do triangles have to add up to be on the inside?
180.
180. So that means when I add these up, this has to be a 30 up here. Because the 70 and 80 make 150, so that makes a 30-degree angle left on the top. And why that's important is because now that we have that's a 30, now I can set the Law of Sine. So if you don't remember the Law of Sine, it's sine of an angle over opposite wall, sine of an angle over opposite wall. That's how it works. So again, this is the Law of Sine. Sine of an angle over its opposite wall, sine of another angle over its opposite wall. Okay, and I'm using X's and Y's and stuff just as generic letters. Okay, Callie, you want to get rid of the computer? Thanks. All right, so let's talk about the numbers that are involved in this one. Okay.
What did you say?
Get rid of your computer.
Oh, I thought you said cover your face.
No.
Oh, okay.
Well, that too. But all right, let's move on. All right, so let's take some of these numbers. So when we set this up, I need, the X is obviously my variable. What is the angle across from it? 30. That's how the Law of Sine works. It's a wall and the angle that's across from it. So when I set this up, it's going to be sine of 30 degrees over its opposite wall, which is the X. That's how the Law of Sine works. It's an angle, a wall across from it. So at least one variable in that problem. Now, on the other side, this is what we call an anchor fraction. It has to have both numbers in it. So what is the other fraction I need to have?
70 and 24.
70 and 24. Sine of 70 degrees over the 24. Now notice, when you write this down, you have to have sine in front of your angles. Don't just put 30 over X and 70 over 24. It's sine of the angle over its opposite wall. Again, it's always an angle and the wall that's across from it. That's called an opposite wall. This will work on any type of triangle. It's not just a right triangle. This is obviously an oblique triangle. Oblique means non-right. This was an acute triangle, and it still works. It'll still find X. My X, I'm expecting X to be a very small number. In fact, it's going to be significantly smaller than 24, just because it's across from 30. Smaller the angle, smaller the wall. So I'm expecting this number to be small, like really small, compared to the 24. So when you start with this number, you go cross multiply and divide. You would start with the number above or below X. So I'm going to start with the sine of 30. You're going to take that times the 24 and then divide by the sine of 70. And make sure, the big thing is, close the parentheses. Super important that you close those parentheses, otherwise the numbers will be all wrong. Okay? So that's the law of sine. Cross multiply and divide. Now if I do this right, this will give me x. I'm going to type this in my calculator so you can see this. So 24 times the sine of 30. I'll show you this here in a second. Sine of 70 on the bottom. Okay, so here we go. Okay, so here's the number. I took 24 times the sine of 30. Notice I closed the parenthesis there. Then I'm dividing by the sine of 70, and I got 12.77 or 12.8 if you round it. So 12.8. So if I go back to my problem here, I said it was going to be small. 12.8. That's really small in this, and that makes sense. Smaller the angle, smaller the wall. That angle is nearly half a 70. So it's probably about half the other wall, roughly. Now it's not a perfect scale, so don't feel like it needs to be exactly. So that's why it's using law of sine. It's not a perfect proportion. They're not linear proportions. Okay, but does that make sense how I kind of showed you the way that's set up, the law of sine? Now it works on any type of problem. It could work for a right triangle, it could work for obtuse triangles. For some people, this is the go-to formula. Instead of doing all the trig functions, they do this on every triangle. It's easy. In fact, I'll show you. I'll do a right triangle here. You could do it on a right triangle and it still works out. Okay, questions with the stuff we did before break, though? That was before, I think that we did that, Wednesday, Thursday, Friday, before spring break? Do you remember that stuff, or you were here? All right, so let's do a right triangle just to prove the point. So, right triangle. Okay. All right, so we got a right triangle here. Throw in some numbers here. So we got a right angle. Let's say, I don't know, my angle could be, let's go 35 degrees. Let's go with, this is my x, and this is, I'll go 15. Just kind of make up some numbers here. I want to find x. You could do the normal trig functions. SOHCAHTOA, you could still do it. It still works. So, for instance, if I want to do SOHCAHTOA stuff, just the old-fashioned, because on a right triangle, SOHCAHTOA works, or Pythagorean Theorem works, if I could do Pythagorean Theorem. On this one, I'm going to probably use the normal sine function. If I was just, thinking about SOHCAHTOA, that this stands for your angle, the opposite wall over hypotenuse. So, sine of 35 is opposite over hypotenuse, which is the 15. Again, opposite is the second letter, third letter goes on the bottom. That's how it always works. How do you solve this? What do we do?
You multiply the 15 over.
Yeah, multiply the 15 across. 15 times the sine of 35, right? That's what we talked about. That was back in chapter 4. We did all those things. This works out to be 15 times the sine of 35. This works out to be 8.6. It's 8.60, so on a calculator. Now that number makes sense because obviously this wall is going to be smaller than the hypotenuse on a right triangle. Now, if you don't like doing SOHCAHTOA stuff, and this is what I was trying to get at over here, if you don't like doing SOHCAHTOA, you could have done the law of sine here on this problem and it would have worked out to be the same 8.6. Just to prove my point, I'm going to do it for you. So, sine of your angle over its opposite wall. So the sine of 35 over x, sine of 90 over its opposite wall. Because again, angle, opposite wall, angle, opposite wall. If I were to cross multiply and divide here, cross multiply, divide, sine of 35 times the 15, divide by the sine of 90, you still get 8.6035, blah, 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 blah. Still the same number in a calculator. It works on every type of triangle, not just oblique. It works on right triangles, it works on obtuse. Some people like that. That makes way more sense doing it this way than doing SOHCAHTOA stuff. because you don't have to label. You just use an angle, opposite wall. You just have to have the numbers filled out. You have to have 3 out of the 4 numbers on that proportion, that fraction, filled in. Does that make sense, the law of sine?
Yeah.
The thing is, what I haven't talked about is like, where did somebody come up with that? Because it's not normal, right? It doesn't look like normal trig functions. Like, how did somebody know that that works? That's something that I want to show you today. This can be tough to kind of watch. Okay, so if you just want to watch this part, I'm fine with that. All right, so here's the idea. There we go. Okay. All right, so if I had a big triangle here, I'm going to call this A, B, and C. So A, B, and C. C is the whole bottom wall. It's not a right triangle. This is just a random triangle. I drew an altitude going down through the middle. That made a right angle down through the center. That was like, it looked like A, B, C, the big triangle, looked like it was obtuse to me. So how somebody came up with it is they figured out the area of a triangle formula for this thing. So what I mean by that, area of a triangle, if you don't remember area of a triangle, area is half the base times height. Right, that's the area formula we talked about in geometry class. That's how you find area of a triangle. Well, my base on this case is the letter C. And then the height, I'm going to call it Z here. That's the height of that triangle. So whatever Z is, you take it times C, and that gives you the area of my triangle. And they figured out that you could get different values for Z depending on which angle you pick. So I could pick this angle right here, or I could pick this angle over here, which is called theta and beta. And what I mean by that is if you went sine of theta, which is this triangle over here, that would be the opposite wall over hypotenuse. That would be Z over A. That's the opposite wall over the hypotenuse. And then they did the same for this triangle over here. They did the sine of beta. The same thing, it's the Z over B. Because that's the opposite and hypotenuse wall on this triangle over here. Because there's 2 right triangles there. And then they just solve for Z. They multiplied this across. So they multiplied the A over. They multiplied this B across. So B times that. And they could substitute those in. So this would be, for the area formula, again, this is how they came up with it. Half times C times A times sine of theta. And they could have also, instead of using that, they could have used the B times sine of beta. And these 2 formulas should be equal. They should be, because they're both the same area of the same triangle. It's still the height times the base. So they set these 2 things equal to each other. So half C times A times sine of theta is equal to half C times B times sine of beta. And what they did is they divided both sides by the same number. Now this comes down to like a law of not the law, but property of equality, where you can do things to both sides of an equation, where they divided both the right and left side by half. They divided both the sides by A, B, and C. All multiply together, because I can choose whatever I want. As long as I do it to both sides of the equation is still balanced. And when you do this, the A's cancel, the C's cancel, this half cancels. On this other side, the C cancels, the B cancels, and the half cancels. And what I'm left with is sine of theta over little b, sine of beta over little a. Right? Well, when you look at the picture, that is my angle, opposite wall, angle, opposite wall. You can see it. That's how they came up with it. it's complicated until you see it, like how it works. This is where it actually originated from. It's come from the area formula for a triangle. That's where the law of sine is. It's sine of an angle over its opposite wall, but it comes from area. Yeah, I never really showed you that. Some people don't need to see that. I think it's important still that you see where some of this stuff comes from, where like formulas originate from, because it's not really complicated if you understand the concept. Like area for a triangle is not hard to think about. Maybe how they come up with the values is, but overall it's not a very difficult problem. All right, questions of the law of sine though. Maybe not this part, but did everyone understand like how I set these numbers up earlier? New thing today. This is the last thing I want to finish with, is called the law of cosine today. So let me scroll down here. Law of cosine. This is the new part that we introduced on Friday, the last day before spring break, and I said we were going to go through it this week. It was just something I wanted to show you. For the law of cosine, it is when you have a triangle, any type of triangle, it doesn't have to be a right triangle, it can be any type, and you have two walls that are provided to you. So let's come up with like two different numbers.
74.
74 and
29.
29. And I have an angle between them. Say this angle is 20, let's go 20 degrees. So this is a 20 degree angle. And I want to find this piece right here, this wall, the wall that is across from 20. This is the perfect thing that what the law of cosine is used for. Now, the reason why it's got to be a law of cosine, I don't have enough numbers to do the law of sine here. Do you agree that I don't have enough angles on that picture to like set up like the proportion? Sine of an angle over opposite wall, sine of an angle over opposite wall. There'd be too many variables because obviously these angles are going to be different. So I don't want to set up that. There's too many letters there. My goal is to find x, not to find beta and theta and all those other things. I can do those later. So we need to try to figure out how to get to x. This is the formula I talked about. It looks like the Pythagorean Theorem. So if you were not here, here's what we wrote down. It looks like the Pythagorean Theorem. The wall you're trying to find, squared, is equal to the other two walls squared added together. So it looks like the Pythagorean Theorem, even though it's not a right triangle. This is definitely not a right triangle. We made up numbers on this. So we set up, it looks like the Pythagorean Theorem, and then behind it we throw a little extra piece, which is the law of cosine part, where you're going to go minus, it's always a minus sign, 2 times the two walls that were provided to you, the 74 and the 29, and then the cosine, the angle that was between them, cosine the 20. That is the law of cosine. It looks like Pythagorean Theorem with one little extra piece, and I know it's not little piece, but this is the little extra piece they subtract in the back. It's got to be the two walls and the angle between them, cosine and angle between them. And if you solve this out, it will give you that wall every single time. Now tomorrow we'll talk about like where they came up with this, because it's way more difficult than the thing I showed you earlier. But let's just go through some numbers. I want to go through a couple examples of this. Now, if you look at your textbook, they have, in fact, if you look at your property sheet has this formula on there. It's right next to the unit circle. Let's get rid of the computer. So we have the unit circle actually has the law of cosine next to it. It's just, I don't like using A's, B's, and C's. I think when people think about that terms, they just get lost. I like to think of like you have two walls, the angle between it. And those are the numbers I plug into the formula. So 74 squared, that's a really big number. 74 to the power of 2, that's 5,476. 29 squared, that's a really big number. Actually not as big as I thought, only 841. And then 2 times 74 times the 29. That's 4,292 times the cosine of 20. Now, back here is where most people get in trouble. It's this part right back here. You have to figure that part out first. And whatever that number is, you have to subtract it. And I'll kind of show you why people get in trouble on that number probably tomorrow. But you got to remember, that number back there is being multiplied before you add and subtract. So 4,292 times the cosine of 20. So make sure your calculator's in degree mode. It's 4,033.16. I'm just going to go 1 or 2 decimal places. So we got to this. We're going to add, subtract straight across. 5476 plus the 841, subtracting the 4,033.16. I'm getting 2283.84. And what's the last step that I have to do here? Square root. So if I take the square root to the other side of 2283.84, this is where you just type it in the calculator. I'm not going to have you simplify that or break it down. I'm not going to have you do that. Just type it in, give me the decimal, 1 or 2 decimal places. So the square root of that number, so 2283.84. Let's see, I typed the number wrong in. 2283.84. It's giving me roughly about 47.8. 47.8. So what this tells me, by just seeing this 47.8, by seeing that number printed there, that tells me, just thinking about this like common sense, this angle right here is got to be really big. Why does that angle have to be really big where that question mark is? Why is this a very large angle? Yeah, the wall across from it is the biggest wall. This question mark has to be probably an obtuse angle, possibly. Now what tells me it has to be obtuse is that this is the smallest wall. This has to be the smallest angle up here. This has to be the smallest angle up there. So if that's smaller than 20, then probably your question mark has to be obtuse. Just think about that kind of common sense in it. So those are like the little things I want you to think about as we go through these new problems. But now this is just the intro day. I just want to kind of intro because I know some people were gone that Friday before, so you never got to see something like this. Maybe you still don't understand it, that's fine. Today is the intro just to show you what to do. But again, you need 2 walls and the angle between it for this formula to work. And how you know to use this formula versus law of sine. Like, I can't do the law of sine here. Like, there was no way I could have set it up. If I could set up the law of sine like I did up here, just do the law of sine all day long. Because the law of sine is the easiest formula we have. It is by far easier. It's just a proportion. Solve it, figure it out. But if you can't do it, then it's probably a law of cosine. That's the only 2 options. There's no law of tangent that I know of. So. Alright, questions so far on the new stuff? Okay, let's do one more problem here. Last problem of the day. Here we go. Last problem. Okay, I need 3 numbers. Give me any 3 numbers we want.
170.
42.
42, I heard 8. 179. 1,000. We're going to make this 42,000. I got to make the numbers at least somewhere close. Okay. Okay, so we made some big numbers, fine and dandy. Okay, we're going to find this piece right here. So to set this up, it has to look like Pythagorean Theorem to start with. So the wall I'm trying to find squared is equal to the other 2 walls squared added together. So it looks like Pythagorean Theorem. Then after that, I have to subtract. I have to subtract in the back here. I have to subtract 2 times the 2 walls. And then cosine the angle between them. And my angle was 8 degrees. Now, am I expecting a big number or a small number before I start?
Yes.
Yes.
Small, why? You're right.
Why?
Why?
Small angle.
Small angle. 8 degrees. 8 degrees is a really small angle. I'm expecting a wall that's very small. I'm expecting it to be less than 42,000. Now, it may not seem small compared to like some of these other numbers in terms of digit, but I'm expecting it to probably be smaller than 42,000. Okay, all right. Now, going through the numbers here. Okay, all right, here we go. X squared, 42,000 squared. So 42,000 squared. Whoa. 1764 1 2 3 4 5 6.
Nice.
Whoa. That's a billion? Is that right?
Billion.
That's 6 zeros. Okay. Now, 179,000
Nice.
squared. Oh my goodness. Okay. 32041. And I got to move it back 6 more spots. 1, 2, 3, 4, 5, 6. 32 billion. Okay. And then we have the minus sign. 2 times the 42,000 times the 179,000. This is 15036. 1, 2, 3, 4, 5, 6, 7. 150 million times the cosine of 8 degrees.
Isn't that 150 billion?
Average at best.
Yeah, it's 150 billion, yeah. Sorry. What did I say? Oh, billion, sorry. Billion. All right. Pretty big number. Now, I still have to take that number times the cosine of 8 before I add and subtract. So taking this times the cosine of 8, that's still a big number. All right. Okay, so here's what I'm getting. X squared equals 1764 1 2 3 4 5 6. Okay. Plus 32 billion 41 million. Okay, and now on the next part, minus, now this number came out to be 1488967 068. 1 2 3 4 5 6 7 8 9 10 11. All right. 148 billion. So if I go across, I think my number is going to end up being negative. So I think that ends up being negative. Maybe I just typed my number in wrong. The problem is probably because the numbers don't work out to make an actual triangle, but I'm going to go with whatever numbers I have here. Or did I write? Oh, I typed in one of my numbers wrong.
Oh no. Oh my god. Which one was it?
The 179,000. Oh, hey, hold on. Hold on.
I think we understand what you're trying to do.
No, hold on. We're gonna fix this problem right now.
Would you type in?
Hold on. Yeah, I added 1 0 too many. All right, here we go. All right, 1488967. 1488967
So we just took off one.
Yeah, I think it was just 1 0. So 1 2 3 4 5 6 7 8 9 10. Yeah. Okay. So hey, fix it. It wasn't in the 150. You know, it was just 1 0 was off. That was fine. That makes a lot of sense. It was just 1 0 off. All right. Now adding and subtracting straight across. So if I add these numbers up, 164,000,000 plus the 32,041,000,000 minus the 148,896,670,680. I think I typed in too many numbers. My God, these zeros suck.
We get the point.
It's a big number. No. 6
Let the man do his math.
2 0 4 1 6 minus 1488967 0 680. Aha! All right. Final answer.
Then. I wish I had a car.
137,533.01.
Did you square it with 8?
I already did.
Okay.
So now why this number doesn't make sense in terms of my numbers, because I kind of get a sense for it when I was typing these numbers in earlier. This number doesn't make sense to me anyway. The reason why this number doesn't make sense, and I think what comes down to it, is that this angle right here is really small. So it's smaller than 8 degrees. Because this worked out to be 137,000. This number right here is 137,000. This number turned out to be 137,000. That was across from 8 degrees. This number is across from 42. It has to be smaller. So it's right. It's just that the question mark that I'm going to find would be a really small angle. It just wouldn't make sense in terms of triangle, but it is this correct numbers. These are correct numbers. They work out to make a triangle.
Can I go to my locker?
So, no.
But I did your math.
Oh, did you? Oh. Yeah, you go. All right.
Sorry, like-
I don't know.